Here we're going to try to show that this series is convergent and find its sum. So this is like what we had started yesterday, where we're going to take this infinity and we replace it with an n, right? And then we're going to do what with the n value? Take the limit as it approaches infinity, right? So to start with, we're taking this and we're going to write it going to n. And we switch our n's to i's for whatever reason, not that that would end up being crazy critical which letters you use, but that's what the book uses. Okay, so first thing I do when I start with this, just to try to wrap my brain around what's going on, is I just start plugging in values to see if I can maybe figure out that this is geometric, and I can just find its sum based off of it being geometric or something like that. This one's not going to work that way. We'll look at it. So if we plug in 1, we get 1 over 2. And I'm actually going to write it as 1 over 1 times 2. Obviously, it's just 1 over 2. And then the next one is 1 over 2 times 3. And the next one is 1 over 3 times 4, and so on, right? Now, is this geometric? So it starts with a half, then it goes to a sixth, and then it goes to a 12th. No, because it's not multiplying by the same amount each time. So we can't find its sum just because it's geometric and using our r value. So we got to come up with a different way, and that's why we're replacing this. So the very last term, if I plug in, n, would be 1 over n times n plus 1, which is, what's in here. So what we're going to do, and these will come up in, I think, a chunk of this homework or maybe a chunk of the future homework, but I think it's this homework assignment. We're going to use partial fractions on this. Okay, so let's just write ourselves a little note. We're going to simplify using partial fractions. So that's what I'm going to do in my next step here. So if I've got this part here, 1 over, doesn't matter if you use the n's or the i's, I and I plus 1. We're just going to do a over I, and then b over I plus 1. So go ahead and do your partial fractions on that, and then you can compare with what I'm getting here. So I'm getting my a to be 1 and my b to be negative 1. And then I'm just going to rewrite what I have up here using my partial fractions. Okay, so I'm starting with I equals 1 up to n. And then instead of this, I'm writing the negative 1 over this piece and the 1 over that piece. So we'll just write it as 2 separate. So we got 1 over I minus 1 over I plus 1. And now I'm going to start plugging them in kind of like I did up here. And we'll see something here that's kind of neat. So if we plug in 1, we're going to get 1 minus a half. Okay, and then we'll plug in the next one. So if I plug in 2, I get a half minus a third. Plug in the next one. We get a third minus a fourth. And then I'm going to do like a dot, dot, dot here. And let's plug in the last one. So the last one is plugging in what? N. So if I plug in n, I get 1 over n minus 1 over n plus 1. Okay, and what's going to happen with this if I tried to sum these up? Does anyone see it? So if we're looking at, like, let's look at these pieces here. Aren't they going to cancel each other? And then look at these pieces here. Aren't they going to cancel each other? Won't that pattern continue? Like, won't this one cancel the next one that's in here, and those will keep canceling? And would this one get canceled or no? Yeah, with the one before it. So everything in the middle is getting canceled. So all that's left is 1 minus 1 over n plus 1. Okay, these are called a telescoping because it's like a pirate's telescope that condenses down. It literally says that in your book. Okay, so these are called telescoping ones. So if they talk about telescoping ones, this is what should happen. It's, you know, this crazy long series here, and then all the pieces are going to break down, and you're going to end up with just a couple pieces left over. Yep. No. Just 1 minus. It's just what's here. So this 1, and then we got the minus here. 1 over n plus 1. Are you thinking because the b was a negative one? We made that a negative because of the negative. Okay, so we changed that plus to a minus. Okay, so now what we're going to do, so let's write this equals 1 minus 1 over n plus 1. And what was the thing we said we had to do with that n then? Take the limit, right? We replaced the infinity with an n, so now we have to let n approach infinity to finish the problem. What do I get if I do this? Just 1, right? Because this piece here will go to 0. So when we find the sum, we just get a sum of 1. Like, a lot of these questions are on multiple choice, so then your work's not super important. You know, if you can do stuff in your head, do it in your head. But if it's a free response, you have to show all of your steps. So that's where we'll do a lot of these questions before our AP test, practicing the free response so you know what's expected to be written down, you know. But I would practice writing these things down, not trying to just do everything in your head. So questions on that? And I don't think I've seen an AP question where they make you use partial fractions within a series, but I know the book talks about telescoping sums here, and that's what's going to happen, or those are going to cross off. You'll see that in college if you take the course in college. So, and it's not like they wouldn't put it on the AP test, I just haven't seen it up to this point. So, okay, we're going to skip this one because it's not something that will be on your AP test. And then this one here is the test for divergence. A lot of people forget about the test for divergence, and the test for divergence is like the easiest test. It usually doesn't work, so you know, you kind of get out of the habit of testing it to see if it works. But when it works, it makes the problem super, super quick. And these will be on like multiple choice questions. A lot of times these type of questions will be the ones where you have I, double I, triple I, and you have to figure out, is I the only one that's true, or are I and double I both true? And so you're trying to do 3 of these in, you know, a matter of a few minutes. And test for divergence is a really quick test. So a lot of times test for divergence is like how you solve one of those 3. So what it says here, we've got a series. It's convergent if the limit goes to 0. It doesn't tell us anything about what it converges to. We just know it's going to be convergent. So our test for divergence, it's on your cheat sheet. So when you print that, this will be on there. But your test for divergence says if the limit does not exist or the limit does not equal 0. So if it doesn't exist, it doesn't equal 0. So that's the main point of it. Then it's divergent. So that's one of those tests where if it's quick to do this test. If it's not quick to do, a lot of times you end up, you know, using a different test anyway. But all we have to do is take the limit and see if it's equal to 0 or not. So we're going to take the limit of what's in here. And we're taking the limit as n goes to infinity, which will be a common theme. We're going to do that a lot. What's the quickest way to do this problem? Divide everything by n squared. So if you divide everything by n squared, that's the quickest way. The other way would be to use L'Hopital's, which is fine. If I divide by n squared, I get 1 on top, and I get 5 plus 4 over n squared on bottom. and this would go to 0, so I end up with 1/5. Is that equal to 0? No, so it does not equal 0. Therefore, it's divergent. And always write by what test you're using. So therefore, it's divergent by the test for divergence. We'll get a lot of other tests coming up. If it's multiple choice, obviously you don't have to write which test you use. You see how quick that is if it's able to be done. Once we introduce all these other tests and we're trying those, sometimes people just forget about how quick and easy this one is, and they end up spending a lot of time on problems that are quick. So, okay, and then the last bit here. Okay, so our theorem here says if we know this sum and this sum are convergent series, if we add them together, it's also going to be convergent. These ands went to the wrong spots. If we subtract them, it's also going to be convergent. You're just subtracting numbers. If you have a constant in there times a convergent series, you can just take the constant out and times it by what the series is. So it's very similar to other rules that we use in calculus. So here we're going to just break this down using our rules up above. So with this plus here, I'm just going to split that into two separate series rather than trying to compute the entire series at once. We're going to break it into smaller ones. And with this first chunk, I'm going to take that constant, the 3, out front, so it's less overwhelming here. So I'm taking the 3 out front. I'm going from n equals 1 to infinity. And then in there I've got 1 over n times n plus 1. Okay, and then this piece back here, I've just got n equals 1 to infinity, and 1 over 2 to the n. This chunk here, didn't we just do that today? What was that equal to? 1. Okay, so this is going to turn into 3 times 1. So if you want to write yourself a note here, I suppose you could write this is from, it's page 3 on my notes. It'd be like the third slide. So we'll just write equals 1 for that chunk. Okay, and then this piece over here, anyone recognize what that's going to be? And we might have done this exact one. Did we do this exact one? We might have. It's not from the first page. No, we didn't do this exact one. Oh, yeah, I gotcha. Yep, from the notes, we didn't do the problem, but I know what you're saying. So this is what type of a series? Geometric. Okay, it's geometric because if I plug in 1, I get a half, right? So this is like where you can start listing them if you need to. If I plug in 2, I get a 4th. Plug in 3, I get an 8th. So you can see that it's geometric. Our R value is equal to a half, and our A is equal to what? A half also. It's just the first term is your A. And then if you remember finding your sum, you'd put what on top? A. And then you divide by 1 minus your R. So we're doing a half divided by a half, which gives you 1, right? So when we're done with this, we just end up with 3 times 1 plus 1, which gives us 4. Questions on that? Okay, I'm going to give you some time then to work on your homework, and I'm sure you'll have questions. If you're not having questions, and maybe you're not trying hard enough, you should have some questions, I think. So there you go. We'll get started on that. So when you're looking at 3, like you're just taking the limit as n goes to infinity. I'll just do it up here, yeah. And what does it say? 2 minus 3 times. And 0.8 is like 4/5, right? To the n power. So if this is a number that's less than 1, as you raise it, oh, thanks. As you raise it, as you raise a number that's less than 1 to an infinite power, isn't the denominator going to get way bigger than the numerator? So what's going to happen to that fraction as you go to infinity? It's going to go to 0, so you just end up with 2 for an answer then. And I don't know if they do anything, super technical in here. No. And 4, same idea. You're just going to do the limit as it goes to infinity, but that one's more like what we've seen a lot of.